Right, in this video, I think this might be a useful video to make because a lot of people struggle with specific heat capacity and latent heat questions. So this is a question I've just done recently with one of my classes, and I think it really hits the nail on the head in about telling the story. Because there's a story to tell in these videos, in this question, because in these kinds of questions, because there is a huge situation that's going on here, and as you can see, there's a vast amount of data that you can often be given, and you've got to unpick that data, and you've got to make it so that that data tells a story that you can then put into an equation to find out what you don't know. So let's have a look at this question first of all. So this question is, in an experiment to measure the latent heat of vaporization, steam at 100 degrees Celsius is passed into the water. The following data are available. We've got an initial mass of the water, a final mass of the water. Now, one thing we can tell about this question is that the mass of the water has gone up in this container. So effectively that's telling us that a certain amount of steam has turned into water. And I'm actually going to make that observation straight away, that the difference between these values is the amount of steam turned into water. So steam into water equals the difference between these two, which is 0.012. So 0.012 kilograms. So that's how much steam has been turned into water as a result of this happening. And we can see here that the initial temperature of the water was 15.2, and then the temperature of the water goes up. So the effect of putting the steam through this water has caused the temperature of the water itself to rise. Naturally, it's caused the temperature of the steam to drop, but let's just have a look at that as a full story now. And it's giving you a specific heat capacity of the water itself. And effectively, we're looking to find out the latent heat of vaporization of water. It's the constant. What we're looking for is the constant L. This L here, because it's vaporization, we're looking for the amount of energy that is transferred when a gas turns into a liquid or a liquid turns into a gas. And depending on whether or not you're going from liquid to gas or whether you're going from gas to liquid depends on whether you're gaining or losing that energy to something else. So if you're becoming a liquid, it means it's losing energy. If you're becoming a gas, it means it's gaining energy. So in this instance, we're going to be observing steam turning into water. So it's the amount of energy that's been lost, because we can see here that it was steam at 100 degrees Celsius and it becomes water, and we had that much steam turned into water. So that's what we're going to find, and this is the value that we're looking to find. We're looking to find out what that latent heat of vaporization constant is. We're not looking to work out the amount of energy for this mass, we're looking to work out the constant, that value of L. Okay, so let's look at this situation as a story. So we've got a container, and in that container we've got our water, the 0.3 kilograms of the water. What's more interesting is that we know that the temperature of this water is 15.2 degrees Celsius. Now somehow we are piping steam into this. Now you could maybe have a pipe that's going into it from a source of steam that's being pumped into there. And so the steam is being pushed in here. So steam is being pushed through that, that tube into the water. And you can almost imagine it bubbling out. And this could happen in any number of ways. But for this, I'm just visualizing what's going on here. So we've got the steam going into the water, and in this circumstance here, it's going to turn, that steam is going to turn into water in this and cause the water level to rise. And we're going to end up with this here. So we actually know that the mass of steam that's turned into water is 0.012 kilograms. And it's useful to draw a picture like this when you've got a big scenario because it helps you to see what's going on. Right, so where do we go next with this? We've got steam going into the water's at this temperature, we've got this mass, and we know this mass of steam is going to be added in. So we've got to look at the situation as a whole. Where is the energy coming from? Well, the energy is coming from, that causes this change in temperature, is coming from the fact that this is steam. The steam, which is at 100 degrees Celsius, what's the first thing that's going to do? Well, steam doesn't drop to 99 degrees because if it's at 99 degrees, it's no longer steam. It's changing state. It would be a liquid, it'd be water. So it's going to go from 100 degree steam to 100 degree water. Still, we're talking about this 0.012 kilograms of steam. So once it's become water, well, let's have a look. What is this relationship here? Well, this amount of energy is the energy lost when it changes state. Well, this is where our final answer is eventually going to come in, because that's an amount of energy Q, which is found by the mass times the latent heat. Well, almost straight away, you'll be able to see that we know the mass, and we want to find out the latent heat. So we're one step closer to solving this problem. But let's analyze the whole thing. Because that's not the only source of energy we're getting here. We're going from steam to water. We're getting the energy that's given off when it drops down to a lower state. So what's now going to happen? The water, this water that's now was steam, is going to turn into water at the final temperature, which is 34.6 degrees Celsius. So we're going to get water that drops from 100 degrees Celsius to 34.6 degrees Celsius. Remember, this amount of water is the 0.012 kilograms. 0.012 kilograms. We'll deal with the 0.3 here in a second. And that is going to be another source of energy, because when it cools down, that's going to give off energy. So that's Q is equal to mc delta T. Some of you may know this as delta theta. It doesn't make any difference. It's just a change in temperature, specific heat capacity equation. So we're going to get an amount of energy from this water, changing temperature, the mass of the water, still this mass, specific heat capacity, it's the specific heat capacity of water right there, and the change in temperature. Well, hopefully you're seeing that the change in temperature here can be calculated from the values that we've been given. So effectively you take 100 degrees, which is what it is, take away 34.6, and that gives you 65.4. So we know that the change in temperature over here, and it's useful to write this down, the change in temperature is 65.4. So we've dealt with where the energy is coming from in this situation, but where's the energy going to? It's got to go somewhere. This energy has to go somewhere. So where's it going to go? Well, it's going to go into this water here. So we've got our source of energy here. Now we're going to identify where that energy is going. So we're going to start at the bottom and work our way up. And we're going to start with water. This is the 0.3 kilogram amount. So this is the water, 0.3 kilograms, starting at a temperature of 15.2. And that's becoming water at what temperature? 34.6 degrees Celsius. Remember, this is the 0.3 kilogram amount. This is the 0.3 kilogram now. We're not talking about the steam anymore. We're talking about the water that is being bubbled into. So all the energy from here is going into this here. And remember, this is just a change in temperature. So the amount of energy going in here is Q, which is equal to mc delta T. Now let's think about that very carefully, about what's going on here. Let's look. We know the mass of this water. We know the specific heat capacity. We know the change in temperature. The change in temperature can be found by the difference between those two, which is 34.6, take away 15.2, which gives you 19.4. So the change in temperature is 19.4. So now we're at a point where we've got all the information and the story told. We can see that the steam is turning into water, and that water is turning into water at a cooler temperature. And we've assigned the energy that's being released in each case. And then here we've got the water turning, the 0.3 kilogram water that was at 15 degrees, increasing its temperature because it's gaining all this energy. So what was given out here is given to this water, assuming that this is a well-insulated container. Now we can talk more in lessons and whatnot about when it's a not fully insulated container, but for all intents and purposes for this question we can assume it's insulated. So we're now at the point where we can start completing an equation to show what's going on.